Hey, I'm Ruby. I just finished my third year at UCLA and I study physics.
What do people say when you tell them that you study physics?
They mostly say why or I'm sorry.
I think people are so scared of it just because other people say it's so difficult.
Since they cannot understand the math behind the physics concepts, they think physics is hard.
I mean, I kind of think anyone can do physics.
They think it's hard, but if they were taught the right way from the beginning, they wouldn't think it would be that hard.
And when we don't have a clear justification for when you can do that or why you can do that, I think students get really put off. Putting the responsibility to make these tremendous jumps on individuals is really driving them away.
I think a lot of physics, the first time I saw it was it was just very, very different and difficult. My senior year of high school, maybe junior year, I don't remember, but we started with kinematics and I had never taken a calculus class before, and I think it was velocity versus displacement. It made no sense to me.
Part of it is just the fact that it's very math heavy. That can serve as a barrier for a lot of students. Or maybe they like something in their physics class and now they're being asked to do 2.5 years basically of mathematics course, and that's pretty dissatisfying.
You have to not have that mindset that it's gonna destroy you.
Societal images in the media, if you look at the Big Bang Theory, and I think that just gets into the public's perception.
Do you watch the Big Bang Theory, John?
I do not. I've never seen a full episode. Sometimes it's on the TV when I walk in the room and I cringe.
If you say biology or chemistry, people have some vague idea of what kind of that entails studying, but they have no idea what physics is beyond the introductory courses.
When I tell people that I study physics, there's often this reaction of confusion and sometimes a slightly visceral sense of disgust. When I started studying physics, I used to think that the only reason why people thought physics was so difficult was just because of what they heard, or they just believed in their mind that they couldn't do it. But after researching here for 9 weeks, I actually really don't think that anymore. What convinced me was doing a math problem in a research paper that I read when I first got here. I decided to ask other people to do this problem, and here's what they did.
Hold on, I messed up already.
I'm not looking at your face because I don't want it to tell me anything if I'm right or wrong.
Can I just tell you the answer?
No, okay, so...
I'm participating anonymously, right?
No.
Do I need to do all the steps, or can I just kind of write the answer?
I'm so lost right now.
I'll work out the steps.
Okay.
Is this supposed to require previous physics knowledge?
No.
Can you see it?
I don't understand how I'm supposed to do this then.
Now I'm curious, how do you think that math and physics classes and math classes are different?
If we have some function of x and y that's equal to a constant a multiplied by x squared plus y squared, one has to find a function f of r comma theta.
Okay, so I'm trying to solve for f of r comma theta.
My coordinate system is x, y. This is r, this is theta.
Is there a relationship between these values, or the constants?
Like polar coordinates?
Mm-hmm.
R comma theta is cylindrical coordinates. I'm guessing I'm not supposed to know that. Probably polar because there's no C.
You're just having me change the variables. So x becomes r and y becomes theta. Okay, do you want me to show you?
Take the first thing squared, the second thing squared, add them together, and then multiply by a.
But I just don't think it should depend on theta because x squared plus y squared is equal to r squared.
It's just making this simple.
So you think x squared plus y squared equals r squared?
f of r comma theta equals a r squared, and it doesn't depend on theta. I would have to say I'm sure.
This is just saying like how big the radius would be for it. F of r theta is just equal to a. This is just algebra.
Skylar, do you believe her?
I believe her. She sounds like she is confident in her answer.
She's totally wrong.
F of r comma theta equals a r squared, and it doesn't depend on theta.
Replicating Dominic's solution, he had two axes, x and y, perpendicular to one another. The point where they meet is typically labeled 0, 0, and is called the origin. If we have a point in the plane, and we want to describe its position relative to the origin, we could talk about it in terms of how far it is along the x-axis, and how high up it is along the y-axis. In that case, we would label this point with the coordinates x, y. We call these Cartesian coordinates. In physics, we often use another type of coordinate system besides Cartesian coordinates. Say we had the same point in space, and we wanted to describe its position once again relative to the origin. We could instead talk about it in terms of its radial distance from the origin, which I will call r, and the angle of that radial line relative to the horizontal axis, which we call theta. And now we can label this point with the coordinates r, theta. These are called polar coordinates. What Dominic did in his solution is he overlaid the Cartesian and polar coordinate systems. The x-coordinate of the point was described by this length, and the y-coordinate of the point was described by this length. Overlaying these two coordinate systems allows us to more intuitively see together they form a right triangle, which we can extract with this length being x, this length being y, hypotenuse being r, the distance from the origin. By Pythagorean theorem, if we square the lengths of the shorter sides and add them together, we get the length of the hypotenuse squared. In the problem that I posed in the beginning, f of xy equals a times x squared plus y squared. And I asked what f of r theta was. Dominic gave the answer ar squared. As a physics student myself, I can say that we use and convert between Cartesian and polar coordinates frequently. Doing so gives x squared plus y squared inherent meaning in our minds as the radial distance squared. So maybe it was the fact that this combination was in parentheses in the original expression, but Dominic took this to be instructions to convert to polar coordinates, which if it were, then the combination x squared plus y squared would in fact yield r squared.
But here's why a mathematician might think that explanation was totally bogus. I'll let John explain to you the math point of view.
Take the first thing squared, second thing squared, add them together, and then multiply by a.
After every single person did the problem, I told them that there was actually another way to do it.
The answer's different.
Okay, I see where you're going.
R is just the distance from the origin, right?
I do not know how I can do this another way.
Wait, why do you get r squared? Well, it's not going to be r squared. It's r squared because that's the diameter.
It's not something that I would have thought of because I definitely thought you were saying to transform into polar coordinates.
Yeah, I don't know.
Okay, do you want me to? You want to know?
Yeah.
Oh, I mean, if I weren't interpreting x and y as being Cartesian coordinates and r and theta as polar coordinates, I would have just said a times r squared plus theta squared.
Oh my god.
Do you know what
that is the wrong way.
That's the correct answer in a very strict sense.
Mathematicians take f of parentheses as literally a set of instructions.
That's just substituting x and y for like r and theta.
So the problem that I did wasn't exactly the same problem that I gave to everybody else. Here's the problem I did, and here's what I changed it to. I changed the capital A to a lowercase f and the capital K to a lowercase a because I thought these new variables would be more familiar to people. Variables like m, cursive L, lowercase r, capital R, these show up all the time in physics. Most of them, depending on context, do have physical meaning. The physics solution to that problem that everybody did was really just based upon this fact that physicists see variables and they interpret them a specific way because they already attach this physical meaning to these variables. Research has shown that in a typical university introductory physics course, about 100 new quantities, which means about 100 new variables, are actually introduced. I think that variables are really useful because they can generalize things in a way that specific numbers really can't. And in physics, this kind of generalizing is useful because physical laws are valid for several different numbers. For example, if we had a car moving on a road and we want to talk about speed, it doesn't matter that the car is going 25 or 60 or 80 miles an hour. All that matters is that it has some speed at all. So in physics, we use generalized numbers and we call them variables. So differences between math, pure math, and math and physics, I would say first difference is physicists use variables to generalize situations. I think I should clarify. Variables aren't actually generalized numbers, but rather I'd say they're generalized quantities. I googled the word quantity. The amount of something usually measured by a number with no reference to spatial direction. But a quantity in math isn't the same as a quantity in physics. In math, we see terms like x feet long, y meters tall, s quarts. Notice how the units are next to the variable. The variable here symbolizes a positive numerical quantity. In physics, quantities look like x, t, m, where x is a measure of length, t measures time, and m measures mass. Numerically, x could be 3 meters, and t could be 4 seconds. The units are implied to be a part of a quantity. An example is the quantity v, which I'll say represents velocity here. Velocity is about speed and direction of movement. V could be, say, negative 3 meters per second. The negative sign here indicates the direction that something would be moving in. So quantities in physics can actually contain information about spatial direction. These types of quantities, by the way, are called vector quantities. Okay, difference number 2. Variables in physics carry implicit units and can reference spatial direction.
Wait, checking units and dimensional analysis, aren't they similar?
There isn't a practical difference. If the units are incorrect, the dimensions will be incorrect. I usually default to units because it's just so intuitive for me.
It certainly doesn't tell you that you're right, but it can definitely tell you if you're wrong.
I do take a lot of engineering courses, and if the units don't match, it's a very good red flag.
Sometimes I think when we force students to do a units check, it's so obvious that may deter them from thinking they're performing just like a useless Mickey Mouse kind of exercise. Asking a student to do it when the student doesn't feel a need to do it makes it seem kind of not really authentic.
A primary method of solving a problem, no, but I use it on every answer I turn in for homework and tests.
What if you give them an actual answer to a question? Don't ask them to actually solve it, but just say, does this answer make sense? Why or why not?
To understand the third difference, or at least what I'm choosing to be the third difference, I think it's important to understand why we use math and physics at all. So when I entered college, my impression of math was just that it was a procedure that we repeated to obtain some final result. This is a page from my first college math book. The procedure for the quadratic formula is laid out explicitly and early in the chapter, and the homework following it requires repeating that procedure to learn it well. In introductory physics, you have nothing like explicitly laid out for you. You really have to look at something and almost like create your own math procedure. Let me try to show you what I mean. In a park, a girl named Clay is standing on the ground at a distance d away from a basketball hoop. She decides to shoot a basketball at a speed v and at an angle theta relative to a direction parallel to the ground. So what is the basketball's horizontal speed when Clay releases it? When Clay releases the ball, it's going to move along an arc. The ball has some speed that carries it upwards, and some speed that carries it to the right, towards the hoop. I'm interested in the length of this arrow, which tells us how fast the ball is moving to the right. That's what's meant by horizontal speed, and I'm going to call it v sub x for the conventional x direction. This setup looks like a triangle to me, and I need to find the length of one side of this triangle, so I'm choosing trigonometry. Cosine of theta equals adjacent over hypotenuse, so v cosine of theta equals v sub x, the basketball's horizontal speed. If that problem were in my college physics class, there would be no directions that said, use trigonometry explicitly. We don't know really if the math procedures that we're deciding to use are definitely going to work. So I think at this stage, verification becomes pretty important. Physics involves creating our own math procedures in some sense. We often verify this math because we want to increase our confidence that we have reasoned sensibly. One cool method of verification that I learned in college physics is something called taking limiting cases. If Clay wants to make the ball into the hoop, she has to at least shoot it in the general direction of the hoop. At the limiting ends of this range, she can shoot it towards the hoop, or she can shoot it straight upwards. If she shoots it straight up at the same speed v, we now have theta equals 90 degrees. We then expect that the ball would have no speed carrying it to the right. Our previous expression for the horizontal speed was found from a general angle theta, and so it should be valid for any angle. When theta equals 90 degrees, v sub x equals 0, and there's no speed in the horizontal direction, as we expected.
No. Sometimes I'll do it, but more often than not, I won't check my answer using limiting cases, although I know that it's pretty useful.
I think they are a very useful and powerful tool, and I do use them all the time.
Is metacognition. It literally means just thinking about your own process of thinking. Things like, how do I know that my reasoning was sound? I view limiting cases basically as a special case of that.
I think it would be really wise to come up with better ways of implementing those kinds of tasks in their homework. They don't have the kind of homework assignments that lend themselves easily to that because they tend to be through an online module.
I think it hasn't been emphasized enough, or also laziness, and I haven't been encouraged to do it a lot.
In a class of 120 students, how do you provide each individual student with an opportunity to consider that and report back on what's happening?
You're given a bunch of answer choice. Someone who's actively doing metacognitive checks all the time will try to find a way to answer the question, how can I be confident in my answer? And limiting cases is a very powerful way to do that.
If your answer does not give you the right limiting cases, means you've done your math wrong or you've made some kind of error in your calculations.
It's like a specific form of the skill of or how to determine if you can have confidence in your answer.
It's better than doing any other sort of tests on your answers.
Okay, so before you decide if you think there's a difference between the pure math and math class and the math and physics class, here are a few more opinions.
No.
Okay.
I also haven't done physics with calculus.
Physics is very, very different. So the fact that we're using all these different letters, that we're graphing things like x versus t, as opposed to like just graphing y and x.
Math is more rigorous, I guess. There are more definitive rules that you have to follow. Physicists have a lot more flexibility to abuse math. As long as it works physically, it's totally fine.
Paper about that, and then
Things you take a whole class and solving differential equations. It turns out in physics, you need to solve like 3 different differential equations, at least in at the undergraduate level. The way you solve a differential equation is you guess for a physics course most of the time. You guess a solution and you check it. That is so deeply dissatisfying, it's hilarious.
Are you being trained to reason about mathematics itself versus in physics being trained to apply mathematical ideas to modeling problems?
Physics needs math, needs mathematics, and mathematics doesn't need physics.
what if the very first time you learned some important say trigonometry concepts and even the most important calculus concepts, you'll learn them for the very first time within a physics class itself. This type of thing, it's called an integrated course, where you learn math in the context of physics, and it was tried recently at a university in Mexico.
There's multiple barriers to this sort of thing, but this sort of thing I can do in my own classes to some degree. Even if these things are covered in other classes, most students don't really understand how to use them when they're applied to other things.
I never put the dots together that I already learned this math portion of the engineering class in like 30 series.
I like the idea of introducing a bunch of like problems that are very concrete, having students try to solve them and presenting some methods for solving that specific problem that end up being calculus. And then once they've seen a few of those, abstract away from that and say, oh, well, you know, all those things you were doing there, that actually has a name that's called the derivative. So you know already how to do derivatives. Let's just now take all these examples you already have, notice that we can unify them under this one umbrella. It's called the derivative and it has these properties as you've seen.
I see. I think that's a great way because most of the things I learned in math classes do not stick to me as something that would be used later in my engineering courses.
It takes an enormous amount of work to design these things.
Because I do already know the math and I kind of understand what's going on in the engineering classes, but if I had connected those dots, it would be a lot easier, like at least twice as fast to learn.
Because I'm sure there are a lot of people who would think that would be an awesome thing to do, and probably even without evidence would think, you know, there's a possibility doing it that way would be a lot better, but they can't. The existing structure is so hard to change.
Thank you to everybody who agreed to interview for my video, and to Nick for helping me film, and to Pranay for letting me use his basketball example, to Dominic and Will for giving me feedback on the content. Thank you guys in general just for being who you are. You made this video what it is.
I'm Nikisha Johnson. What do you want, like school or like major?
Yeah, pretty much.
I'm a dual major in math and physics at the New Mexico Institute of Mining and Technology.
My name is Dominic Diaz, and I am an applied math and physics major at UCLA.
Warren Christensen. I'm an associate professor of physics at North Dakota State University.
Dr. John Buncher, and I work in the physics department at North Dakota State University.
Nick Kuhn, Department of Physics, Kent State University.
Hi, my name is Morgan. I'm at UCLA and my major is molecular bio.
My name is Adesh Pratap Singh. I am a third-year mechanical engineering major at UCLA.
So the paper was, I forgot to ask Josh to introduce himself. If you're watching this, Josh, I'm sorry. I think you're awesome.
Hello, my name is Katie. Hey, my name is Kalra and I'm a secondary science education major. Hi, my name is Stephanie Berg and I'm a chemistry major over at University of Minnesota Morris. Hello, my name is Katie Slack. I'm a wildlife fisheries and aquaculture major from Mississippi State University. I made a D in physics.